Okay, we are already 5 minutes late. So let's get started. We'll continue the discussions of alcohol from where we left. We talked about the structural properties of alcohols. We looked into the hydrogen bonding, and we learned this bits and pieces of nomenclature of alcohols. And as I mentioned, I have recorded some lectures before and I have placed them online for deeper discussions on those concepts. What I'm trying to focus in class is mostly on important concepts. So if you want to have more detailed discussions, please visit the lectures that are available online on my courses. So today we are going to talk about synthesis of alcohols. Then we'll come back to the reactions of alcohols sometime later. Okay, let's try black color. So how do we synthesize alcohols? We already learned that alcohols are those compounds which have hydroxy groups attached to either sp3 carbon, or enols are those which have hydroxy groups attached to sp2 carbons. Phenols are those which have aromatic rings as parent hydrocarbon. This is sp2 carbon, but this is part of an aromatic ring. So these are called phenols, these are called enols, and these are simple alcohols. So these alcohols can be classified as oxygen containing functional groups, right? And as a result, when you are looking into synthesis, you got to think of either oxygenated compounds as precursors, or you have to think of the methods to add hydroxy group from some other source. For example, if I take an alkene and if I want to make alcohol out of it, I can make two types of alcohols here. Let's say I want to make non-Markovnikov type of alcohol. I want to make a primary alcohol. So what do I do here? Hydroboration, right? If you do hydroboration, essentially you are adding water, but you are taking the help of hydroboration reagent system. First you add B2H6 and then sodium hydroxide to get rid of the boron, and as a result you add water across the double bond, but the hydroxy group is going to the terminal carbon. We can make primary alcohols out of it. If I have to make a secondary alcohol out of this very alkene, I take water and acid, I just do the hydration of alkene, and I end up with Markovnikov product, and that's what you learn in Chem 251. You can make alcohols from alkenes by addition of water. So we are starting with a non-oxygenated compound. We are bringing oxygen in the form of water. That's one way of making. There are various methods for synthesis of alcohols that we will be talking about today. So if you have already come across some ways of making alcohols, you should recollect all of them and try to. I will be trying to shift back and forth between the PowerPoint and this, because I don't want to use a PowerPoint because I want to draw them on the board. At the same time, I cannot draw everything out. So when there is something that we can quickly review, we will shift back to our PowerPoint that's already placed on my courses, so you have access to this. I don't want to install any updates. Okay. What are the discussions? Something that I can help with? If it is something related to things that we are discussing, you would rather discuss combined. If it's something that you can wait, you can probably discuss after the class. Okay, there must be some doubts cropping up in your mind, but you cannot get distracted, because while discussing that doubt you miss some other concept, and it's distraction for everybody. So alcohols can be made by various methods from alkenes that you already learned in Chem 251. If you have an alkene of this kind, this is cycloalkene, but nevertheless you can do oxymercuration and you can get the hydroxy group. You can do hydroboration, you can make non-Markovnikov type of alcohol. And when you have prochiral double bond, why do we call this as prochiral double bond? Because I can make chiral compound out of it. So that's the reason why it's called prochiral compound. though it's not quite chiral yet, but that if that is used as a starting material, I can make chiral alcohol. Whereas I don't call this double bond, this is not a substituent, as a prochiral double bond. Even if I make something out of it, the compound is not going to be chiral because there is symmetry here. Whereas in this case, you have a double bond which is asymmetrical. One of them is disubstituted, the other one is monosubstituted alkene. So if I do any reaction on this alkene, I am going to get chirality out of it. Whether I get chirally pure or racemic, I don't care, but I am not going to get one compound, non-chiral compound. I always generate a chiral center. That's the reason why these alkenes are called prochiral alkenes. When you have prochiral alkenes, you normally end up with racemic products. If you have some chiral control instead of just boron, if I use chiral boron, the chiral boron reagents available, I can make this alcohol in a stereoselective fashion. So we already learned how to make alcohols in Chem 251. We are just reviewing it. But since you learned already what is the chapter called stereochemistry, you should also be looking into the stereochemical outcomes. Not only the chemical outcomes, but also the stereochemical outcomes. That's what we learned in SN2 and SN1 reaction, right? Everybody is substituting a given group with something that is a nucleophile, but you are ignoring stereochemistry. You cannot afford to ignore stereochemistry. Chemical outcome is important, and the stereochemistry is also important, right? Even if you write correct structure, if you don't depict the stereochemistry, you lose importance, right? So as you proceed along in organic chemistry, you need to integrate whatever you learn at various stages. Okay. So this is prochiral double bond, and one can make chiral alcohols out of it if you take a chiral borane. For example, there is a borane called camphenyl borane. It comes out of camphor. I'm not sure if I can draw the correct structure here, but that sort of borane, let's say we have something like this. This is a chiral source for a boron, so the boron would deliver from only one phase because the other phase is blocked by some methylene group. So this would have facial selectivity, and if you draw a three-dimensional diagram of this molecule, it has two phases, right? The boronating agent would attack from the less hindered phase, and as a result you would get chiral alcohol. Anyhow, the essence here is to talk about the synthesis of alcohols. Couple of ways that you already learned are listed here. If you want to make diol, you take osmium tetroxide. This is not quite prochiral, so we don't get chirality here. However, this could be cis or trans. These two hydroxy groups could be pointing on the same direction of the ring, or one could be pointing away and one could be pointing upwards, right? So once this is a trans diol. If you want to make a trans diol, you go through epoxide formation. MCPBA is a reagent that is used for formation of epoxide. And that epoxide can be opened with water, so the water would attack from the opposite phase, from one phase, and this oxygen would go to the opposite phase. So you get two hydroxy groups facing away from one another, right? So you can make trans diols, you can make cis diols, you can make simple alcohols if you are given with alkene, right? If I want to make a ring opened alcohol, what do I do? Let's say I want to make an alcohol which has been ring opened. Let's see, how can I synthesize this compound from that alkene? What do? I have to open this ring, right? I do the bosanolysis, then I do the reduction. We already learned redox, right? If you are at a higher oxidation level, you just use a reducing agent, you go to the lower oxidation level. If you are at a lower oxidation level, use oxidizing agent, you can oxidize it. So alcohols can be oxidized to carbonyl compounds. Carbonyl compounds can be reduced to alcohols. So, depending upon what you have in the hand and what you need to make, you choose your reagents accordingly. So, if we have an alkene, then if you want to get a diol of this kind, then we do a ozonolysis and do a sodium borohydride reduction. We'll talk about what is sodium borohydride in a minute. So, you can make alcohols. And you can do hydrogenation. When you do the hydrogenations, pi bonds are reduced. Why do we call this as a reduction? Because we are adding hydrogen. Addition of hydrogen is reduction, right? Removal of oxygen is reduction. Removing the number of bonds to oxygen is also reduction. So we are adding hydrogen across this pi bond. As a result, we are taking a carbonyl compound down to an alcohol. We'll have to use some metal mediated hydrogenation. In this process, any other pi bonds also are hydrogenated, so you get saturated alcohols. So in summary, alcohols can be made in variety of ways. In this class, we would only look into details of those methods that you haven't learned before. Why do we need to learn synthesis of alcohols? Alcohols are important intermediates in organic synthesis. If you have an alcohol, you can convert alcohol into any of these groups that are listed here. You can make an alkyl halide, you can make an ester, you can make carboxylic acid, alkenes, ketones, aldehydes, ethers can be made. The other way around is also true. Alcohols can in turn be made from any of these groups that are listed here. What do I do if I have to make an alcohol out of an alkyl halide? I just substitute with hydroxide, right? You just have to see what is in the product, what is in the starting material. If something is missing, that needs to be brought as a reagent. Hydroxy is missing in the alkyl halide, so I bring hydroxide as a nucleophile and knock the chloride out, right? Halide out. So I do a substitution reaction. If I have an aldehyde or an ester, I do a reduction reaction, right? So alcohols are very important synthetic intermediates or synthetic reagents, building blocks in organic labs, so or in organic synthesis in medicinal chemistry. So we need to learn as to what are the reactions of alcohols and how do we make alcohols. So one of the things that we are doing right now is to learn how to synthesize alcohols. So when you talk about synthesis, we often use a word called retrosynthesis. Retrosynthesis is opposite of synthesis. When you talk about synthesis, you have a starting material and you want to get to product. You have a reagent or you have a reactant, you have product, right? And then you need a solvent and you need to adjust the conditions. And there's something called workup. We'll talk about the workup later on, but these are essential components of synthesis, any synthesis for that matter. Okay, it doesn't have to be alcohol synthesis. We always start with something, we add something to it, and the starting material becomes product. That's why we call this as a reactant. Whatever is that helping the conversion of starting material into product is called reagent. They cannot alone react by themselves. They have to be brought into contact with one another. So we use solvent. Solvent should be something that facilitates interaction of reagents in reactions. Works as a medium. After the reaction is done, the medium is removed. Right? That's called a solvent. Depending upon the reaction that you have, solvents are chosen. Right? If you have an SN1 reaction, you choose polar solvents because polar intermediates have to be formed. If you have SN2 reaction, you don't want polar intermediates to be formed, so you use non-polar solvents. Some cases we use protic solvents, some cases we use non-protic solvents. We'll talk about the solvents in a little more detail when we get to some of the reactions. So coming back to retrosynthesis. Opposite of this exercise is called retrosynthesis. In other words, planning. Retrosynthesis is not done in a flask. It's done in your mind, your paper, and you are just mapping out as to how to make your product from what you have. You have a starting material in the synthesis, but you don't have starting material to begin with in the synthesis. You are only asked to make alcohol, so you have choices for starting material. Somebody can make this alcohol from an alkene, someone can make this alcohol from some other source like an aldehyde or a ketone or ester. So various synthetic chemists are different on their own thinking, so they can come up with their own method. That way of coming up with a method is called retrosynthesis. In retrosynthesis, we are trying to identify the starting material in a reverse way. It's like taking driving directions. I want to go to Boston and I'm in New Bedford and I have many choices. I can go to Providence and then go to Boston, or I can go on Route 24 on the other side, right? So what I mean to say here is, when you have one goal in your mind, you can identify your starting material. And in this case, we already have starting material because we are in New Bedford. That's our starting material. So from New Bedford to Boston, how do we go? What reagents do we use? What intermediates do we get? All that's called retrosynthesis. Taking planning synthesis out on the paper. So that's very important because in the lab you cannot just jump and try and mix everything and anything and try to make the compounds, right? So the planning has to be done. In this case, this alcohol can be made if I have this aldehyde. I just need to bring in the hydride. This process is called retrosynthesis, and this double-headed arrow is used. whenever you see this kind of an arrow, that's retrosynthesis. That's something you have to understand. You cannot use this arrow and say that this is retrosynthesis. That would mislead. People would think this compound is going to that compound if you use this arrow. So if you want to show the retrosynthesis, use that arrow. Okay? So in retrosynthesis, I can break anything. Like say for example, I can break this bond and see how to add hydroxide. Or I would see how to add hydride. Or I can try and see addition of R minus. There are so many ways. I can disconnect this molecule in 3 ways and then come up with 3 ways of synthesis. In one method I am trying to add hydroxide, in the other method I am trying to add R group, in one of the methods I am trying to add hydride. So whatever I am trying to add, and I subtract that, and whatever the rest of the piece of the molecule has to be your starting material. For example, here I am disconnecting at this spot, so I am trying to add hydrogen as a hydride. So what should be the rest of the piece? The rest of the compound should be a double bonded compound. I am trying to add H minus, so this has to be delta positive. So I take an electrophilic carbonyl compound and then try to add the hydride. If I want to add the R group as a reagent, then I go with something of that kind, because this does not have R group, so now I can add R minus to this and I can make alcohol out of this thing. Or if I don't want to add any R minus or H minus, I would like to add hydroxide, then I go with an alkene and do the hydration. See how you think? Okay? Is that clear? How to plan a synthesis if you are confronted with a molecule. You are asked to make a molecule. You take a deeper look at your molecule, think as to how to make that alcohol or whatever the material that you want to make. What bond can you disconnect? To do that disconnection or to carry out that disconnection in synthesis flask, what reagents do I need? So all this is called planning, and that planning is called retrosynthesis. It's done in a backward way. You are looking at your product and from there you are trying to see your starting material, right? So in the synthesis, you start with starting material and you go to your product, right? The synthesis is done in flask, retrosynthesis is done in your mind or in your paper, okay? So in today's class we will see how to make alcohols out of addition of hydrides. If I take carboxylic acid, if I do one reduction, I remove one molecule of water or one oxygen, so that's called reduction. I go to a stage called aldehyde, and if I further add hydride to aldehyde, I go to alcohol. So these are various oxidation levels. This is at a lower oxidation level than this one, this is at a lower oxidation level than this one. So depending upon the starting material that I have to choose the equivalents of reducing agent, for that matter any other species that I want to add. So let's say I have an aldehyde, I want to take it down to alcohol. What are my choices? I just need to supply a hydride. If I have a hydride, this bond is polarized because of the electronegativity of the oxygen. That's delta negative, that's delta positive, and I have negatively charged species, so this acts as a nucleophile and that goes and adds to this pi bond, and as a result carbon gets pentavalent, right? So pentavalency is not accepted for the carbon, so one of the bonds has to be broken. So I push these electrons onto the oxygen and I write the product of this. Or we had carbon that in turn was attached to oxygen, but one of the bonds got broken, so one of the pairs of electrons moved on to the oxygen, so oxygen gets a negative charge, and there was hydrogen attached to that, so that hydrogen is left, and I'm adding this hydride, so I'm making it a little bold. This hydrogen is this one, okay? So this was an sp2 carbon, and now we got an sp3 carbon. This is called the tetravalent tetrahedral intermediate. That's always invoked when you have addition to carbonyls. Carbonyl group is made up of an sp2 hybridized carbon, but upon addition of a nucleophile to an electrophilic carbon, this pi bond gets broken, breaks itself, and the electrons are polarized onto oxygen because another bunch of electrons are coming and attacking here, right? So this carbon cannot take all the electrons and still keep one oxygen. It can only accept 4 bonds, right? So you get an alkoxide, and that alkoxide, when you add water, gets the proton. Here the water is not shown, but you have to have a reducing agent. That's the first step, and a solvent, and then finally you add water. This addition of water is called workup. So when this water or any protic solvent is around, this alkoxide is going to attack the hydrogen of water, If you write water out, that's water structure. Water can act as a base or acid. We talked about it yesterday. So this alkoxide is attacking the hydride and the electrons are pushed onto the oxygen. As a result, you make this alcohol plus hydroxide. Got it? So if you have an aldehyde, you just need to add a hydride to make a primary alcohol. I cannot make a secondary alcohol out of hydride. By addition of hydride, I can only make primary alcohol because it already has one hydrogen and you are adding another hydrogen, so that carbonyl carbon becomes CH2. When it is CH2, we call it as a primary alcohol. We'll talk about how to make secondary alcohols out of it. Even if I start with carboxylic acid, I end up with primary alcohols because first addition of this hydride would take me to aldehyde and then another hydride would add, that would go to all the way to alcohol. What sort of reagents do we use to carry out these reductions? We'll look into that. Okay? So anyhow, even if you don't know what reducing agent is being used here, the reducing agent is the donor of hydride. Anything that can donate hydride is called as a reducing agent. Okay? We have various types of reducing agent. Aldehydes upon reduction give primary alcohols. Ketones upon reduction would give secondary alcohols. Why secondary alcohols? There are no hydrogens attached to this carbon and you are only adding one hydride. You cannot add two hydrides to this because the valence is already satisfied when you add one hydride. So you get secondary alcohol. And when you have esters, you can add two hydrides, you get primary alcohols. When you have carboxylic acids, primary alcohols. When you have acid chlorides, you get primary alcohols. All these have something common in all the structures. What is that commonality? A carbonyl group. And what else is common? A hydride. A carbonyl group can be reduced to a lower oxidation state by using hydride donor, depending upon the substituents that you have in your carbonyl compound. Either you end up with primary alcohol or secondary alcohol. If you have two R groups on the carbonyl carbon, you get secondary alcohols. If you have one R group, you get primary alcohols. For example, if I had a propanaldehyde, I can make propanol out of it, right? I just need to add hydride. If you see one hydrogen in parenthesis, that is hydride. Okay? If I have to add hydrogen, then I need to have a metal. This is not quite hydride. It's a full molecule of hydrogen. Okay? This is hydride. Okay? So let's see how do we go about. This is not moving. Okay, some of the reducing reagents are listed here. It's ridiculous, it's not moving. Okay. So these three species that I have listed here are normally used as reducing agents. So you just have to remember these reducing agents. It's sort of like a wild card. You can throw it any reduction that you want to do. Any problem for that matter. But some are more selective, some are more powerful than others. Okay? Sodium borohydride can only reduce sodium borohydride. This is boron, it's hydride of borane, so it's called borohydride. Borane is BH3, right? And if you add one more hydrogen to boron, that's called borohydride, and it's an anion, and so it has to have a counter ion, and this is sodium borohydride. The counter ion does have some role, but there are various types of borohydrides. You can buy lithium borohydride, calcium borohydride, sodium borohydride, all of these one and the same. What's the active species? The active species is this borohydride. The counter ion alters the activity to some extent. Some are more powerful than others, but you cannot completely change the nature of this reagent from an oxidizing reagent, from a reducing agent to an oxidizing reagent. What this all does is it supplies one hydride to whatever that requires, like aldehyde or carbon, right? So this is lithium aluminum hydride. Aluminum is more powerful Lewis acid than boron. So this reagent is much more powerful. And again here we have lithium as a counter ion. This itself is more reactive, so we don't need to substitute this for any other counter ion. Here we go with the lithium or calcium as we need it. Okay. Anyhow, lithium aluminum hydride is more powerful, so we have to be more careful when you use this in the lab. So normally you are given a sodium borohydride in organic class because this is safe. You cannot have an explosion out of it, or it doesn't take off. on you. Okay, but when LiH is used, it can run away, and as a result, you can lose your compound. Your reactions could be messy if you don't control the temperatures. When you use LiH, we normally do it at 0 degrees and then slowly bring it to room temperature. This essentially does the job of sodium borohydride, but this is much more powerful. So borohydrates, sodium borohydrates are used when you have aldehydes or ketones. Sorry about it. Because these are more electrophilic, even if the reagent is milder, they can be reduced. What do we get out of the reduction of aldehyde? We get a primary alcohol, right? And we get a secondary alcohol out of the reduction of carbonyl compound. So you take aldehyde, you mix with sodium borohydrate in some protic solvent, you get primary alcohols. If I have an ester, that's an ester, right? And this electrophilicity of this carbon is not as much as the electrophilicity of this carbon here. The aldehyde carbon is more electrophilic than ester carbon, because the electrophilicity is dependent on the delta plus. The extent of this delta plus is dependent on what is attached to this carbon. Here we have a hydrogen. My hydrogens are weird, right? So anyhow, this hydrogen is not as electron donating as this oxygen. Oxygen has two pairs of electrons, so, and there is an electron deficient carbon, so there is always a possibility of donation of this pair of electrons to this carbon. That's called resonance, and that resonance makes this more stable. Something that is more stable is less reactive. Stability and the reactivity are inversely related. Okay, anything that's more stable is less reactive. So if it is less reactive, this would not cut the job for you. You will have to use stronger reducing agent. So we use lithium aluminum hydride. Lithium aluminum hydride is more powerful, so you can take down this carbonyl compound all the way to the alcohol. If you have two carbons, you would still have those two carbons. What is being removed here? Some of these oxygens have been removed, so that's called reduction. In the process, we are also adding hydrides, right? We are adding two hydrogens, and those two hydrogens are coming from lithium aluminum hydride. We'll talk about the mechanism in a minute. Okay, so can we use lithium aluminum hydride for reduction of aldehydes and ketones? Why not? We can use it, but that's like shooting a mosquito with a gun. You don't need that powerful reagent, right? You can get away with sodium borohydride. It is more inexpensive, more safe to use, and it works fine with aldehydes and ketones. So we don't quite use lithium aluminum hydride for that. But if you don't have sodium borohydride in your lab, you can just use lithium aluminum hydride as well. But I cannot use sodium borohydride for the reduction of esters because it's not powerful enough, right? So you can go from stronger reagent to the weaker substrate, but not the other way around. If you have a weaker reagent, you have to have a stronger reagent. So I don't know whether I'm confused on that. So let's talk about what is the role of Diboll in a minute after seeing the mechanism of this reduction. There are some examples here. If you have a benzaldehyde, you can make benzyl alcohol. This aromatic group is an R, right? It doesn't have any role in it. You can simply say that as an R group. Just that the reactivity might be different. Some might be slower, some might be faster, depending upon the size of the R group, depending upon the nature of the R group. We'll talk about that in chapter 19. But let's say we have an aldehyde here, and we have another aldehyde. This is methylaldehyde, and we have a trichloromethylaldehyde. Which one of these two is more electrophilic? Which one of these two aldehydes would react faster with sodium borohydride? It's an aldehyde, is also an aldehyde, just that it is attached to fluorine, so the R group is much more electron withdrawing. As a result, you increase the delta positive sign of the electrophilicity of this carbon. Electrophilicity is affinity for electrons, is increased because of this electron pulling towards it. Here we have just methyl group, so this is not as electrophilic as this compound is. So just that the rates would differ, but the outcomes would not change. You always get a primary alcohol out of aldehydes. You can always use sodium borohydride. And why do we use protic solvents? Some of these are inorganic salts. If you use hexane as a solvent, it would dissolve polar compounds, polar solvents, right? At the same time, we don't want to use water because water would react with sodium borohydride. So we strike a balance and we use some protic solvents like alcohols. kind of water, at the same time kind of hexane or alkane. It has both hydroxy group and a methyl group. So it's kind of suitable solvent for reduction, but you cannot use methanol when you use LAH because LAH would react with methanol. You have to use non-protic solvent. Lithium aluminum hydride is called LAH because that's abbreviation, right? Sodium borohydride you can call, I don't know, sodium borohydride. That's the shorthand form for sodium borohydride. Lithium aluminum hydride has two shorthand forms. You can write LiAlH4 or LAH, okay? And the other reagent that I showed you in the previous slide is called diabol, diisobutyl aluminum hydride. We will get to that in a minute. So let's look at the mechanism of sodium borohydride reduction. Sodium has is a counter ion here, so that does not participate much in here. So the carbonyl is electrophilic and the hydride is attacking there, and as a result this pair of electron is moved, and that can be donated to sodium plus, or it can be on itself O minus because the electrons are moved into oxygen, and when you add water or methanol that would pick up the proton and that would become an alcohol. So hydride is coming from boron reagent, that hydride, and that hydrogen what is attached to alcohol, oxygen, is coming from water. So essentially you are adding two hydrogens, right? Two. One of them is coming as H minus, one of the other one is coming as H plus. H minus is coming from borohydride, H plus is coming from water. In total you added a molecule of hydrogen. Just that you didn't use a molecule of hydrogen, you used a hydride and a proton. So in essence you added one molecule of hydrogen across one pi bond. I could do this very reaction if I had a palladium carbon and this hydrogen gas. Right? Hydrogen gas is a little dangerous to keep in the lab, so we'll see. Go.
Sorry, the second one that's adding the H plus, what is that called?
This is called proton.
No, what is adding the proton? You said that
Proton is coming from water.
comes from water and then
Yeah. See, this pair of electrons is now acting as base, and this water is acting as an acid. It's donating the electrons to the hydride, and this bond breaks, so that becomes a hydroxide. And at the end of the reaction, what would be the nature of the reaction medium? It would be basic because you have hydroxide, you have sodium, they would find each other. Sodium hydroxide is your byproduct, right? In organic chemistry, we just focus on organic compounds. We don't balance the equations, we don't worry about the inorganics, sometimes we don't even worry about the byproducts. We will just focus on the major product, okay? Unlike inorganic chemistry, that's something you have to. Any questions as the reduction of aldehydes and ketones? This mechanism is valid for ketones also. You just have to substitute one of the R groups, one of the hydrogens with R group. This is the benzophenone now, whatever, depending upon what is this R group. And this is a ketone, and the hydride can be added and that can be made into a secondary alcohols. So you have to remember, carbonyl compounds give various types of alcohols. Depending upon the hydrogen content of your starting material, you can get different types of alcohols. If you had one hydrogen on the aldehyde, you can make primary alcohol. If you didn't have hydrogen attached to a carbonyl group, you would get a secondary alcohol. What would I get if I use a formaldehyde? Formaldehyde is made up of one carbon. Two hydrogens are attached to carbon. So if I add one more hydrogen to it, because I am doing a reduction, I would get methanol out of it. Right? So this is also a primary alcohol. So depending upon the hydrogen content on the carbonyl compound, you end up with. Okay, so that's what we are trying to do nowadays. We are trying to produce our fuels by reducing carbon dioxide. If you take carbon dioxide or carbon monoxide for that matter, if you add some reducing agent, you can essentially convert that into methanol. Well, I'm trying to write CH4. Okay, so thereby you can recycle your carbon dioxide. You can produce alcohols. Alcohols like ethanol can be mixed with alkanes, petroleum gas, and you can have alcohols running on it. So that's a big research. We are trying to reduce the pollution and recycle the carbon dioxide. But what is the problem here? This is not as reactive as aldehyde, so your lithium aluminum hydride or sodium borohydride will not reduce carbon dioxide that easily. So we have to have more stronger catalysts. Research is ongoing on that part. Okay, I just thought of mentioning that. So this is retrosynthesis. So now we had a starting material, sorry, we had a product in mind, and we do the disconnection of the hydride, and that hydride can be brought in the form of sodium borohydride if I have to identify a carbonate compound. So this is the reverse process. I am trying to make this alcohol and I am planning it out as such as this process is shown here. So I am identifying what I need to add. This is not commercially available. You cannot buy a hydride by itself because it doesn't exist. It exists only in the form of sodium borohydride. This is donor of hydride. So I buy sodium borohydride and I buy the respective ketone of the aldehyde, and then I add hydride to that and make alcohols. Right? So if I want to make this alcohol, I add sodium borohydride to this aldehyde and I can make this alcohol. Blue is coming as hydride. This is coming as a proton. So this proton is going to the electronegative atom, the hydride is going to the electrophilic atom. Okay. Any questions? Can I reduce ester out of sodium borohydride? No, I cannot reduce. So when I have multifunctional group containing compound, and if I have a milder reagent, I can do selective reduction. I can only reduce this carbonyl compound and I still can keep my ester. So there are some advantages for sodium hydride for being mild. You can have selective reducing capacity. You can selectively reduce one of the functional group over the other functional group. That's called chemoselectivity. Okay? Sometimes we need to keep the ester intact. We don't want to lose this ester functionality that is very critical for the drug activity. Let's say this is some drug, you want this ester, so you don't want to shoot this with the lithium aluminum hydride. If you were to use lithium aluminum hydride here, all the functional groups would be reduced, and as a result you would get a diol. This would go to alcohol, this also would go to alcohol. That's no good for you. Sometimes milder reagents are good too. You don't need to reduce all the functional groups, and you can use selective reducing this. Lithium aluminum hydride is not very selective in that matter. So for example, this slide illustrates that. If I have this functionality in my starting material, I have a double bond, I have a carbonyl, I have a carboxylic acid. I want to just reduce the carbonyl, which is a ketone, not the carboxylic acid. So I use sodium borohydride. If I want to go to a diol from here, then I use lithium aluminum hydride. Both of them have some workup stages involved. Here we use methanol or ethanol as a solvent. Here we use this reagent in some solvent which is called tetrahydrofuran. Tetrahydrofuran is just a solvent. Okay, it's like an ether. What is ether? We'll talk about ether functional groups. This is called diethyl ether that we use in the lab. So you take ether as a solvent, add your substrate, and slowly add lithium aluminum hydride, which are solids. These two are solids, so you can add pinch wise or portion wise. Okay, and after the reaction is done, in the second step you add water or a little bit of acid so that you supply the protons. Okay, so the hydride is added here and the hydride is added here. So 3 hydrides have come from lithium aluminum hydride. 2 protons have come from water. Okay, so this is called workup. This is the reaction, and this is the reactant, and this is the reagent, and this is the product. Okay, sometimes we have to control the temperature. Right, you have to look into the thermodynamics of the reaction and see if it is an exothermic reaction, you need to cool. If it's an endothermic reaction, you need to heat. I'm going to skip this slide because we already talked about dihydroxylation mechanism, right? We were talking about mechanism of reduction of LAH of an ester. How does it go all the way to alcohol, right? So we will take one ester, simple ester, and then we'll apply to lactone also. So let's take one of empty slides if I have. Let's say we have this ester. This ester is made up of propionic acid and an alcohol pod. If you mix acid and alcohol, you make esters. We'll talk about that when we get to esters, but esters are used as a reagent here. A reactant. We are not talking about the chemistry of esters. We are talking about the chemistry of esters as a method to make alcohols, and out of this we get that alcohol. 1, 2, 3. I need to have the count of carbons. If I have started with 3 carbon containing ester, I get 3 carbon containing alcohol. This is not featuring in the product, so we need to know where is it gone, and how does hydride add, and why do it add twice. Okay, so that's the mechanism part. So I'm going to use LAH for this because sodium borohydride doesn't do it, cannot do it, right, unless you take it to some 200 degrees or 300 degrees, and then probably it would work. Okay, so when I use with hydride reagents, I don't have to use all the species to show that hydride is attacking here. I would just use hydride because that's the hydride source. That's all it's doing. So I can start with a hydride. That's my nucleophile, and it's giving to the electrophilic carbon. Carbonyl carbon is electrophilic, and as a result it breaks one bond. Whenever you make a bond to a tetrahedral carbon, you have to break a bond. Okay? Remember that. So hydrides, the curved arrow, this is called curved arrow. It always starts from electron rich place and goes to electron poor place. Okay?
So
And
Professor,
yeah.
what's adding that H minus?
LH. Okay? It can add 4 hydrides. So you don't have to use all the LHs in the reaction again because it becomes too big a structure. You use power. I would take it even if you just hydride because it's all giving just hydride. Right? There are some more things we learn in advanced classes, but at your level this is enough. Hydride is adding to the carbonyl and oxygen is getting polarized and it's getting the intermediate. So let's write the intermediate product. This is not curved arrow. This is just straight arrow. Okay, reaction arrow. And I'm getting something here, and my oxygen is getting polarized, getting the electrons, and it had an oxygen, and I added hydride. So I made a bond, and I broke a bond. I broke one of these pi bonds because I made one sigma bond to the carbon. Carbon is tetravalent here, and it's a tetravalent species here. I had a methoxide on my carbonyl. I still have the methoxide. This is called the first step, the tetrahedral intermediate. So always you have to get your tetrahedral intermediate. It's normally charged on oxygen. Okay. So this is called alkoxide at times, but in this case we still have an ethyl group. So what this is not very stable species, so it doesn't wait for you to add water. It just kicks back these electrons. The electrons are repolarized into the space between the carbon and oxygen, and as a result this carbon again would make 5 bonds. It cannot do the 5 bond valency, so this takes off. This ethoxide takes off. It's leaving, so it goes away. When it's going away, I can just show the arrow into the empty space. There's nothing here. That means these electrons are moved onto oxygen, or you can just show it outside. I could have used a small arrow to push the electrons onto oxygen. This is good and this is good. Whichever you want to stick, you stick with one of them. So what is this ethoxide doing? It's a leaving group. Ethoxide is stabilized by itself, so it can survive, so it's leaving. So as a result, what did I get? I lost this ethoxide. These electrons are pushed into the space, and as a result I made my pi bond back, and one of the bonds is now broken. Whenever I make a bond, I break a bond. That's something. If I am not using anions or carbonium ions, okay? I am using a carbon which is already tetravalent. That's all you can go maximum on carbon. So you have to maintain the tetravalency, right? So as a result, I made aldehyde. This aldehyde is more reactive. So again, another hydride adds to this. Where is this hydride coming from? Again, it's coming from LAH. LAH has 4 hydrides, so it can keep on giving 4 times, right? And as soon as this aldehyde is formed, it doesn't wait for anything else. It just undergoes hydride addition, and as a result, one of the bonds is moved back onto the oxygen, and I add another hydrogen. This was the first hydrogen that we added. Let's say this one, and now we are adding another hydrogen, which I am adding square. So the second hydride is adding. Okay, this was added in this step. Now we are adding another hydride to aldehyde, and as a result, we make tetrahedral intermediate. But this tetrahedral intermediate does not have any leaving group. Leaving groups are normally heteroatoms: oxygens, nitrogens, chlorides, bromides. Those are leaving groups. If you have carbon-hydrogen bond, this is difficult to break. Carbon-oxygen bonds are difficult to break, and this just stays and waits for you to add water. That's when you just do the workup. Finally, once you know that your starting material is consumed, you take a TLC, right? You look for the disappearance of your starting material, and if no longer the starting material is available, you can just go ahead and add water, and that water would supply proton to this. This would pick up one of the water hydrogens of the water, and as a result, you make one more carbon. Okay. So what did I do? I added 2 hydrides and I reduced it to a primary alcohol. So esters accept 2 hydrides from LH and they go all the way to primary alcohol. What if I want to add, what if I want to stop at aldehyde stage? If I want to stop at aldehyde stage, I should take only one which has one hydride. I should not have 4 hydrides. If I supply only one hydride, I can stop it here. And for that, I use something called diisobutyl aluminum hydride. It has a diisobutyl group and it has only one hydride. So for selective reduction of esters to aldehydes, I use dibol. That is the sense of dibol. Dibol is somewhere milder than LAH, but it's stronger than sodium borohydride. So you can selectively make it. Okay? We'll continue the discussion in the next class. You had a question? Yeah. And I'm going to place this very video online again. If somebody wants to review it, somebody missed it. Yeah, we do. On chapter 13. The 2 people.